Hey everyone, this is Andrew, and in this video we're going to cover a basic heat transfer problem, in particular this one right here. So what we have is a plane wall, which is at a temperature T1 over here, temperature T2 over here. It is L thick, and it has a thermal conductivity of K. So I have all the constants defined over here, and with any kind of heat transfer problem, or really any kind of thermodynamics or any kind of really engineering problem, you have to make assumptions in order to make your equations valid. So we're just kind of assuming that this plane wall, so this is like a two-dimensional cut. So the wall, the long section is going in and out of the page. So like let's say for example this is the inside of a house and this is the outside of a house, just for example. Although 50°C inside would be kind of warm and negative 20°C outside would be pretty cold. So just for example, it's a plane wall, it's going those two directions, and it's at steady state, everything. All the usual assumptions you will have for a problem like this in a class. This would usually be one of the first subjects you'd cover in a heat transfer class too, so it's kind of a good starting place if you're trying to get some extra problems. So we're trying to find Q prime prime, which is just basically the amount of energy per meter squared. Since we don't know the actual length or height of the wall, we can't find the energy going through it in terms of watts, which is joules per second. So we're finding it in terms of energy per square meter. So if you're looking to learn how to solve a problem like this and you're in a heat transfer class, you probably have seen the equation already for it. I'm not going to go over the detailed math and all the assumptions to derive the equation. I'm just going to kind of show you what the equation is and how you can use it. So the equation that we use for this is Q double prime, which is just in watts per meter squared, so it's the energy rate per meter squared, is equal to negative K dt dx. So this is just the rate of temperature in terms of the thickness of the wall. So it's just, you could really, since we don't have any heat generation going on, it's just constant temperature going through the wall, we can actually rewrite this as negative K times delta T over delta X. So that just means just an average, the temperature distribution is just a straight line, so it's a linear temperature profile. And then since now it's just a delta instead of a differential, we can actually figure out what this delta T, delta X is. So that's actually going to be our first step. So delta T, delta X, and what is delta T? Since heat always flows from hot to cold, we'll assume our direction is going to be from hot to cold. So T1 is our hot wall, T2 is our cold wall, so the heat is flowing in that direction. So this is the final direction, and this is the initial direction. So we're just going to say delta T is T2 minus T1. Keep that as delta X for now. And that's just going to be negative 20 minus 50 delta X. And that's going to be equal to negative 70 degrees C over delta X. So what is delta X? Well, in this example, our delta X is just L. So I defined a little coordinate frame here, just saying this is 0 and this is X equals L. So our delta X is just L. So L, which is 0.25 meters. And that is our number. I'll do the math later to actually get the number. So at this point, we have K, we have delta T, delta X, and we're trying to find Q double prime, so we can already do that. Q double prime is equal to negative 50 watts per meter Kelvin times negative 70 degrees C over 0.25 meters. Alright, so now that I punched in all the numbers, the answer I'm getting for Q double prime is equal to 14,000. Now, we know what the units are in watts per meter squared, but just as kind of a good practice, the way that I always check my units is that I actually will do them out. So in this case, we have our watts. That doesn't cancel out with anything. We have a meter and a meter, so that's going to be the meter squared. Then we have this Kelvin on the bottom, and we have this degrees C on the top. Now, since we're taking a differential of temperature in this previous case, it is correct to write this as degrees C, but it's also correct to write it as Kelvin, because the difference between 2 degrees in Celsius is the same as the difference in Kelvin. So if you're multiplying temperatures, it's a good idea to first convert them to Kelvin, but if you're just taking a difference between two temperatures, it really doesn't matter. I could get into that much more, but I don't want to get off topic here, so I'm just going to leave it at that. So this really is also a Kelvin, because we're taking that temperature difference and we're not multiplying temperatures. So that Kelvin is going to cancel out with this Kelvin, and we're going to have watts per meter squared. And just to kind of make it make sense in your head of how the units work out, that's how the units work out. And that is our answer. So let's say we also wanted to kind of think of what the temperature distribution is inside of the wall. Now for this case, it's really easy because we already said before that it's a plane wall, it's at steady state, all those assumptions that we would do at this point. So we know that T1 is at 50 degrees C. And I'm not going to, break out a grid and make everything look perfect here. But let's just say, this is like 0, negative 20 is like about there. And so we already talked about how it was a linear temperature distribution, but that is going to be the temperature distribution inside of the wall. And the heat flows from the hotter side to the cold side at 14,000 watts per meter squared.